Hello everyone. Today our topic in discrete math course is summations. First, regarding the notation, to express the sum of the terms am plus 1, etc. an, we use the notation I equal m to n a sub I. We can use instead the index j, k, etc. And this is read as the sum from I equal m to I equal n of ai. And this represents am plus 1 plus etc. plus an. The index of the summation I runs through all integers starting with its lower limit m and ending with its upper limit n. For example, to represent the sum 1 plus 2 plus 3 etc. plus n, we can use the notation I equals 1 to n I, or for example I equals 0 to n minus 1 I plus 1. For example, the sum of the first 100 integers 1 plus 2 plus etc. plus 100 can be represented as the sum I from 1 to 100 of I, which is known to you even from the school, n multiplied by n plus 1 over 2. Here 100 multiplied by 101 over 2, which is 5050. So the sum of integers starting from 1 to n equals n multiplied by n plus 1 all over 2. The usual laws for arithmetic applies to summation. For example, when a and b are real numbers, we have the summation j from 1 to n axj plus byj equals to a, the summation j equals 1 to n of xj plus b, the summation of j equals 1 to n yj, where x1, x2, etc., xn, and y1, y2, etc., yn are real numbers. Next example, find the summation from j equal 1 to, for example, 5 of j squared. This is equals to 1 square plus 2 square plus 3 square plus 4 square plus 5 square, which is 1 plus 4 plus 9 plus 16 plus 25, which is 55. Next theorem, if a and r are real numbers and r is not equal to 0, then the summation j from 0 to n a multiplied by r to the power j equals ar to the power n plus 1 minus a all over r minus 1 if r is not equal to 1. If r is 1, this summation equals to n plus 1 multiplied by a. To prove this, let Sn equals summation j equals 0 to n ar to the power j. To compute S, we multiply both sides by r and manipulate the resulting sum as follows. The right side equals sum j equals 0 to n a r to the power j plus 1. And by shifting the index of summation with k equals j plus 1, we'll have the summation k equals 1 to n plus 1 a r to the power k, which is equals to summation k equals 0 to n ar to the power k plus ar to the power n plus 1 minus a. We obtain this by removing k equals n plus 1 term and adding I equals 0 term. This equals to Sn. These two parts are equal plus ar to the power n plus 1 minus a. So RSN equals Sn plus AR to the power n plus 1 all minus A. Solving for Sn shows that if R is not equal 1, then Sn equals AR to the power n plus 1 minus A over R minus 1. If R equals 1, then Sn equals summation J equals 0 to n A R to the power J, which is the summation J equals 0 to n of A, which is n plus 1 multiplied by A. Hence proved. Next, some useful summation formula. Summation K equals 0 to n A R to the power K if R is not 0 equals to A R to the power n plus 1 minus A all over R minus 1 if R is not equal to 1. Summation K equals 1 to n of K equals n multiplied by n plus 1 over 2. And summation K equals 1 to n of K square equals n multiplied by n plus 1 multiplied by 2n plus 1 over 6. Summation K equals 1 to n of K to the power 3 equals n square multiplied by n plus 1 square over 4. Summation K equals 0 to infinity of x to the power K if the absolute value of x is less than 1 equals 1 over 1 minus x. Summation K equals 1 to infinity of K multiplied by x to the power K minus 1. The absolute value of x is less than 1 equals 1 over 1 minus x all square. And last example for today, find the summation K equals 50 to 100 of K square. K equals 1 to 100 of K square equals 2 K from 1 to 49 K square plus K equal 50 to 100 K square. K equal 50 to 100 K square equals the left part K equal 1 to 100 K square minus this part, which is the summation K equals 1 to 49 K square. Using the formula K equals 1 to n of K square equals n multiplied by n plus 1 multiplied by 2n plus 1 over 6, we obtain the summation K equals 50 to 100 K square equals 100 multiplied by 101 multiplied by 201 over 6 minus 49 multiplied by 50 multiplied by 99 over 6. You can easily do that, and the final result is 297,925. For today, that's all. Thank you.